Start the recording and okay.
There we go.
Okay. Hi everyone, welcome again to CosmoLATAM seminars. Today our speaker is Gabriel Marin, an incoming PhD student in University of Turin. He's going to present his the work that he did in his master's. The title is Schwinger-Keldysh Cosmological Cutting Rules. Please, Gabriel, you can start.
Thank you, Mateus. So hello, everyone. You already heard it. So the title of my presentation is Schwinger-Keldysh Cosmological Cutting Rules. So this was the work that I did in collaboration with Francisco Clippi, Gonzalo Palma from University of Chile, and Francisco Rojas from Adolfo Baños University. So again, this was the work that I did in my master's. Okay, so let me begin. So here's the outline that I would like to follow during this talk. So first, I would like to do a very brief quantum field theory review. So I'm going to touch the basics of it. Then I'm going to talk a bit about unitarity, both in flat space and in de Sitter. And then I'm going to describe briefly the Schwinger-Keldysh diagrammatics. And finally, I'm going to move on to start cutting diagrams in this framework. Okay, so let me start with a question. So a quite hard question to answer in cosmology is, what was the origin of structures in the universe? As I said before, yes, this is a quite hard question. However, correlation functions in inflationary cosmology might have a hint. So here I'm primarily referencing to spatial correlations between cosmological structures at that time, correlation functions, in a theory of exponential expansion of space-time in the early universe, inflation. So the important claim here is that if inflation is correct, then we can trace back today's galaxy distribution that we can see in the first picture to correlations when the first atoms were formed and the first light was released. And what cosmologists are trying to do is to find out a theory with correlations that consistently evolves to the one that we actually observe. Okay, so we'll be working with at this epoch over here. Okay, so a correlation function, we typically think of it in the following way. So they live on these equal time boundary where we can take it to be tau equals 0. And a main difference to standard flat space amplitudes is that, of course, all the final states are located on a single time slice, which in this case correspond to the future time slice. Okay, so we specifically say that cosmological observables or cosmological correlators are given by the equal time expectation value written in this form, where the Q is a bunch of field products, the tau is the conformal time, and the omega is typically taken to be the vacuum state for the interacting theory at conformal time minus infinity. So here we can see that as a main difference, that we're going to see it in a couple of minutes, that we have these two cuts over here that they're repeated. Okay. So now let me briefly shift the attention to start discussing a bit about the basics of quantum field theory, which is needed in order to compute cosmological correlators. Okay, so QFT, we know that it's a tremendously powerful tool as it unites quantum mechanics and special relativity. And it has, of course, applications in many areas of physics. So one of the objects of theoretical interest in quantum field theory are scattering amplitudes, which are described by the S matrix in the following way. So amplitudes are basically telling you the probability transition of an in state into an out state. And it allows to obtain probability prediction of some particle collisions. Therefore, they provide a strong connection between theory and experiment. So for instance, we can perform test predictions of the standard model Lagrangian by looking at the data collected at the Large Hadron Collider, or LHC, at CERN. Okay, So now these instates, we think of it as some collection of wave packets coming from temporal negative infinity. We have the collision occurring at time equals 0. And then once again, the final out states are once again some collection of wave packets. Okay, so we represent this picture, this bus picture with the following drawing over here, and we call it a Feynman diagram. While the object in the top, we refer to it as amplitudes or correlation functions. Technically, so here's an important disclaimer. Technically, amplitudes and correlation functions, they're not the same object. However, we can go from one to another by using, for instance, the LAZ reduction formula. All right, so now how do we actually compute these amplitudes? Well, in standard quantum field theory courses, we first are going to start by discussing what are the physical principles we would like these amplitudes to obey. So generally, we're going to be interested in looking at locality, causality, unitarity, and certain symmetries. And from this point, we can construct Lagrangians, we can derive equations of motions, and we can draw Feynman diagrams in order to compute amplitudes in perturbation theory. So, and the important point, which is the interesting point here, is that they're actually connected to the physical observable. So for instance, take cross-sections. One of the most important ones in particle physics is related to the amplitudes by just squaring it and adding some extra factors. Okay, so from this point on, we're going to be interested in looking at the consequences of imposing some physical principles. So particularly, I'm going to be interested in looking at the unitarity part. All right, so in flat space, this is nowadays referred to as generalized unitarity. However, I'm just going to mention the unitarity consequences that were derived back in the 60s. So it's a set of some nice constraints that are imposed on the amplitudes by imposing unitarity on the S matrix. So we first start with these the composition of the S matrix. So we write it as 1 plus AT, where this 1 corresponds to the Fourier scattering, and hence no collision at all. And the T corresponds to all the interesting corrections that we want to compute. So now the unitarity condition reads as follows. So it's just S dagger S equals 1. And by imposing it, we can obtain this simple yet insightful equation. So on the left, we can recognize a discontinuity operation. And on the right, we have just a multiplication of T dagger times T. Okay. So now, unfortunately, we do not know the full exact value of this T. Instead, we understand this equation order by order in perturbation theory. So let's take a look on how do we do that. So for instance, consider a theory where a 2-to-2 particle interaction is permitted. So then we're going to be, we have to discuss about this T4, so a 2-to-2 particle collision. So we're going to, what we do is to essentially write it order by order in perturbation theory. However, we can also categorize it by a certain type of drawing, which is called a Feynman diagram. So this first one is called the tree-level diagram, and it has order d squared. This one, the next one, is a one-loop diagram, has order d4, a two-loop, and so on and so forth. Okay, so if the theory also permits a 2-to-3 or 3-to-2 particle interaction, then we also need to discuss about this T5. So, and it also has its own infinite series expansion in the coupling. So yeah, that was what I wanted to mention there. Okay, so just to simplify things, I'm gonna wrap everything up. I'm gonna denote this T4 with this number blob, and T5 it's also we're gonna do the same. Okay, so then let's apply these same thinking and understand the above equation order by order in perturbating theory. So the left-hand side, so the discontinuity operation, it's just gonna be the sum over all the tree-level, one loop, and so on and so forth. So this is given by the fact that the discontinuity operation is a linear operation. And on the right, we have to recall that it was T dagger times T. It's going to be a bit more different because we have a multiplication of infinite series. So if we want to understand it order by order, we have to be just a bit careful on the coupling. Okay, so in this setup, if we want to take a look at the lowest order non-zero term, we're going to see that it's composed by the discontinuity operation of a one-loop diagram, and on the right is going to be this product. So just g squared and g squared here of a tree-level diagram. Okay, so we say that the discontinuity of a one loop corresponds to a multiplication of two tree-level amplitudes. Okay. So, and there is a nice interpretation on what's going on. So we think of it as follows. So here's the discontinuity of a one loop diagram. So this discontinuity, what it's doing is to essentially cutting through this internal propagator and setting the external legs on shell. So then the result is, of course, a product of two tree-level amplitudes. So then you can generalize this statement, and this was done by, they're called the cutting rules, and this was done by Katkusky in the 60s. So yes, there is an incredible coincidence in the name. And you can also obtain something that is called the generalized optical theorem, which I'm not going to mention here. But yeah, it's something that you can do by imposing unitarity. Okay, so now the story in cosmology is a bit different because we can still try to apply the unitarity condition. However, we're missing one element, which is the S matrix. So I'm not going to go into huge detail on why we do not have an S matrix in a standard way in cosmology, but yeah, there's something that is something that's missing. However, if we impose the unitarity condition to the evolution operator, we're obtaining this equation over here, which resembles a lot the flat space case. And so well, with this expression over here, we can still obtain similar expressions. So we can obtain something that's called the cosmological optical theorem, which was done by these authors over here. And then we can ask ourselves, well, are there any cutting rules by using this equation over here? And this was done by Melville and Paget in 2021. And they used a formalism which is called the wave function of the universe. Well, so there's another quite popular formalism in cosmology, which is called the Schwinger-Keldysh Bathynian formalism. And we can ask ourselves, are there any cutting rules in this framework? So this is precisely what we tackled in this work. So first, allow me to briefly review the Schwinger-Keldysh Bathynian formalism. So as the name suggests, a Bathynian formalism can be done to the correlator. I'm not going to go into a lot of detail on how do we obtain this expression, but yeah, you have to do a couple of Gaussian integrations. You have to insert a complete basis of states in a smart way. But yeah, you obtain this expression over here. And after, of course, a bunch of algebra. So the important highlights of this expression over here is that we now have two types of fields. So we have a phi plus and a phi minus, one going forward in time and the other one going backwards. And so yeah, this is a new introduction. Recall that we only had one field. Recall that this Q over here was a product of a bunch of fields, phi. So we do not measure these two different fields at the boundary. We only measure one. And this is solved by this delta function over here, which is fixing this phi plus and phi minus to be the exact same. Okay. So from this point, we can construct a generating functional, and it's written in this way. And you can, of course, compute amplitudes by just taking functional derivatives of this expression over here. Okay, but you have to keep in mind that we now have two different fields, phi plus and phi minus. Okay. So now let me move forward and discuss the Feynman diagrammatic rules of this framework. So we have two key elements. So the first one are vertices. So since we have two different type of fields, a time order one and an anti-time order one, I'm gonna denote them by this black dot and this white one. I'm gonna be smart and write the combination of these two with this shaded vertex. So this vertex over here, we can attach many external legs as we like to this one. So for instance, the diagram that is displayed on screen corresponds to the linear order term of the this correlation over here, this phi to the n. So also these white squares over here, they corresponds to the value of the field at the boundary. So if you recall, there's no difference between phi plus or phi minus, or in other words, there's no difference between black or white in the boundary because of the delta function that I showed you before. So I'm gonna denote it with a square. Okay, and of course, in order to write this diagram, we do require this following interactive term in the interactive Lagrangian. All right. So the next key element that we require are called propagators, and there are two kinds. So the first one is called the bulk-to-bulk propagators, and there are lines connecting two vertices. So of course, each vertex can be either black or white. Therefore, we have four possible outcomes. And they have this following mathematical value that you can see on the screen. And something interesting is that there's the presence of these Heaviside step functions over here. And so they're mainly the reason, well, this is one of the reasons on why there sometimes is quite complicated to obtain analytical results in on these formalisms, because you have to perform some nested integrals at the end of the day. Okay, so and the next elements in the propagators are called the bulk-to-boundary propagators, and they're essentially lines connecting vertices to squares, and they have this simple expression over here. All right, so we're almost ready to start taking the discontinuity of different diagrams. We just needs a proper definition for the discontinuity operation. So we're going to take the following one. So given a function f that depends on a collection of momenta and a collection of three momenta, we're going to take the discontinuity with respective some momenta that we write down at the bottom of the discontinuity operation to be equal to the same function plus its complex conjugate, while interchanging the momenta that is not being advertised at the bottom of the discontinuity operation. And there's also the addition that we have to flip every single three momenta. So an example to understand that what's going on here. So consider a function f which depends on four momenta. So we have k1, k2, k3, and k4. And let's say that we want to take this continuity with respect to 1 and 4, just hypothetically. So this continuity is going to be the same function plus the complex conjugate of the function while interchanging k2 and k3, and also flipping the signs of every single three momenta. All right. So something that you could say that could be bothering you with this expression is the fact that a usual definition of a discontinuity operation contains a minus here. And yes, that is true, but this is only to keep some signs, because if you add an extra I, an extra imaginary unit, both inside and outside of the discontinuity operation, you're going to have a minus sign over here with an overall minus sign. Okay. So they're essentially the same. There's just a sign difference. Okay. Great. So let's start to think of taking the discontinuity. So the simplest diagram that we can take this operation to is the following tree-level S-channel contribution. So if you're taking a quantum field theory course, you might recognize it. So of course, each vertex can be either black or white. So in this diagram over here, it corresponds to actually the four diagram summation on the right. So it's going to be a bit more difficult if we start to consider decomposing diagrams in this way, because the number increases quite rapidly. Actually, it increases to the power of v, where v is the number of vertices. Something that we can do is to work with a more primitive object. So we're going to call it in this way. So we're going to do a summation over the color of the vertex or of the vertex. And this is going to be our primitive object over here. So in a mathematical way, we perform a summation over A and B, where A is plus and it can be either plus or minus, or in other words, black or white, of an object that I'm going to call to be this calligraphic A. Okay. So once again, the calligraphic A by itself, it doesn't mean anything. We know that the correlation function is the sum of this calligraphic A. But it's going to be easier to work with this object. So yes, the line of thought that they're going to follow is to first compute the discontinuity of this calligraphic A and then perform the summation. And this is something that we can do because the discontinuity operation is a linear operation. Okay. So as I said before, we're going to work with this object over here. Okay, so we're interested in computing the discontinuity. So typically we take the discontinuity along the internal channel, so this S quantity. And as expected, the discontinuity is only going to affect this internal term over here. So let's take a zoom in to look at what's going on. So by taking the discontinuity, we're going to find that this bulk-to-bulk propagator is going to be written as 2 times the real part of the function, the bulk-to-bulk propagator. And by using some complex number properties, we can rewrite it as the following sum over here. So it's going to be a sum of a product of 2 times the real part of a bulk-to-boundary propagator times the real part of another bulk-to-boundary propagator. And we have to add this imaginary part of these bulk-to-boundary propagators with the addition of these sign vertices, so these index vertex. So none of these index signs, the A and B. Okay. So now we can ask ourselves if we have the same interpretation as in flat space, where by performing the discontinuity operation, we have some products of lower point diagrams. So and the interpretation is also valid here. So at least diagrammatically at the moment. So yeah, where these H value here, so the green value is just corresponding to the real part of a bulk-to-boundary propagator. And this one in purple is the imaginary part. Okay. So now it would be really nice if after taking the summation over the sign vertices, so if they're black or white, basically, it would be really nice if on the right part, these terms reduce it to be the correlation function or the discontinuity of these correlation functions. It would be really nice. So this is the mathematical value of the last expression, which was only diagrammatically. So it will be really nice if we take the summation of this A and B, we reduce it to some correlation functions. So the first line is truly going to yield the correlation function because it's literally the definition. So nothing weird going on here. However, the second line is going to be a bit more problematic because there is a presence of these little A and B. So they're changing the sign when taking the summation. So in order to still rewrite this as a discontinuity of some correlation functions, we're going to introduce a new object, which we call the BART correlators. So BART correlators, they appear naturally when studying the complex structure of these correlation functions. So for instance, take this 3-point correlation function. If you write it in terms of this calligraphic A that I presented before, you're going to see that we can rewrite it as 2 times the imaginary part of this calligraphic A with fixed vertex index, so with this fixed A. So this hints that it could be something interesting going on with the remaining complex part, right? So in other words, the real part. So this is precisely what the bar correlation gives you. So if you introduce a small a, which is changing the value, it's just changing a sign, you're going to see that by using, again, the same complex properties, you're going to see that it can be written as 2 times the real part of the same calligraphic A with the same vertex fixation. So this also suggests that we can generalize the construction of the bar correlators. So this is something that we also did. So here's a generic endpoint. So in this case, yeah, it can be endpoint correlation function. So this is the bar correlation function definition. The problem is that when you start increasing the number of external points, you can also take different bar correlations depending on how many internal A's you insert here in the sum. And well, turns out that they're all connected to each other by just performing this real and imaginary interchange. Not going to go into a lot of detail on how do we perform this, but yeah, there's a connection between those. So yeah, the important take here is that bar correlators, they appear to be well, they actually are a non-observable term. However, they're actually connected to the observable by just performing this real and imaginary interchange. And they find out to be quite useful because they're literally what's going on this second line in the past expression. So at the end of the day, by performing the discontinuity, we were presented with this expression. So this is written in terms of correlators and this new expression, the bar ones, which are related to the actual observable. All right. So this is the simplest diagram that we can compute. So the fun starts when considering more challenging diagrams. So we start considering what I like to call it, the V-vertex linear chain graph. So it just consists on taking the S channel, so rotating the right part and attaching a bunch of copies on the right. Well, how many? Well, since we want the name, it's in the name, right? We want a V number of vertices. And if we want even more generality, we can consider the number of external fields or external legs to be arbitrary. So for instance, for the first vertex, we can have B1 external lines connected to it. For the second one, we can have B2 external lines all the way to B sub V. And they can be either different from each other, they can be equal, depends completely on the theory. We wanted to be completely general about it. Okay. So of course, we're interested in computing the discontinuity along the internal tunnel. So S1, S2, all the way to S sub V minus 1. Okay. And so the result when taking the discontinuity is the expected one, meaning that we have to consider a bunch of terms. So for instance, one that we have to consider is cutting through this first internal line. We also have to add the contribution of cutting through the second internal line all the way through the last one. And we also have to consider multiple cuts. So when we cut all internal lines, when we cut all except for the second one, all except for the first one, and so on and so forth. Okay. And something that was quite challenging was to write this into mathematical equations, but it can be done. And it has this following expression. So I know that it looks quite cumbersome to see, especially at first glance. However, I can tell you some highlights of these 4 lines over here. So the first highlight is, oh, sorry, let me mention previously that this is this continuity for the calligraphic A, and of course we know that this is not the observable. However, we can take the summation over all the value of the vertices, of the color of the vertices, and we're going to obtain a similar expression, but instead of this calligraphic A, we're going to have now the correlation function on the left, and a combination of regular correlators and barred correlators on the right. So now the highlights of this expression over here is so first, the sum over here is a sum over a power set, meaning that we have to consider, well, this is basically telling you that we have to consider every possible cut that you can think of, basically. So the first line and the last one corresponds to taking a cut through in the diagrams that are located on the edges. And these two middle lines correspond to taking cuts when needed to the subdiagrams located internally. Okay. And yeah, so this second sum is just telling you when to consider a bar correlator and a regular one. Okay. And this big I over here is just an imaginary factor. All right. So let's take an example. Let's do an example to understand the power of this expression over here. So consider the following V equals 4 correlation function. So it has 3 internal channels, S1, S2, and S3. So let's take this continuity. Of course, it's going to have a bunch of contributions. I'm just going to analyze 2 contributions. So the first one, let's say that we want to cut through this first internal line, so through S1. So the interpretation is exactly the same as we understand in flat space. So we cut through this internal line and we set the external legs to be on shell. Well, in this case, set the external legs on the equal time boundary. All right. So when we do that and we apply this formula in the top, it's going to pop out this term over here. So essentially, it's telling you that we have a combination of 2 terms, product of a three external leg element here in the left, and a 5-1 on the right. Okay, and we also have to consider the contribution of the barred version of this expression. So a different cut that we have to consider that is also present is when we also cut through these last line, so the S3 channel. And the interpretation was also the same way. So we cut through it and we set the external lines on the boundary. So now when we apply the above formula, we're going to have these more difficult expressions over here. So we're going to have the product of this contribution times the contribution on the other edge. And we're going to have also a double discontinuity of this subdiagram in the middle. So this is needed because we're performing 2 cuts. And we're going to have a different combination on regular and bar correlators. And we have to recall that they're actually connected between each other. All right. So this was this was done all at tree level. So let me briefly mention. Let me briefly do a comment on loops. So a simplest version of a one-loop diagram that we can construct is to take the original V-vertex linear train graph and to attach an internal line on the right of the V vertex and connected it to the first vertex over here. So this is going to form a closed loop. So this is the a more precise picture of what's going on. And if we perform this continuity operation, the interpretation is quite nice, and it's kind of similar to flat space, where we now have as a result of the discontinuity operation, we're going to have that the loop diagram decomposes into products of tree-level diagrams. So which is kind of nice thing to have, because generally computing a loop diagram is more complicated to compute a tree-level one. At least in flat space, I would say in the series they're both complicated. Well, and this is given by the fact that we can rewrite the one loop integral in this following way, that it kind of looks a bit more difficult rather than writing it in a standard manner, because we have a bunch of integrals. However, this is the easiest way to see that this continuity operation is not affecting this integral over here. Well, it's just it could pop out a different minus sign, but there's not nothing going on internally here. All right. So, and to finish, let me say some concluding remarks. So what we did in this work was to study the cutting rules for the Schwinger-Keldysh path-integral formalism in cosmological contexts. We analyzed the external, the V-vertex chain graph, and a one-loop case. And some of the main important properties that were required to during the computation were this one. So this is the first one. It's the behavior of the bulk-to-bulk and bulk-to-boundary propagators well, when we imposed a sign change into the momentum. So an important thing to say here is that this is valid for massless particles. For the massive cases, a bit different. And the second important property is the following one, which allows us to write the real part of a bulk-to-bulk propagator into products of real parts of bulk-to-boundary propagators. So this literally allows you to cut and set the lines on shell. Okay. So something that we can do in the future is to explore these new types of these bark correlators that were introduced. They kind of form like a complete basis when in an linear algebra point of view, when we also consider the regular correlators. But yeah, this can be done in the future. And yes, so this work we expect to upload it to the archives soon enough. So yeah, so that was the end. So thank you very much for your attention, and I'm happy to take questions if you guys have one.
I will speak. You listen to me?
Yeah, I can listen to you. Yeah. Hello.
Yeah, great. Yeah, good to speak. Written for the speak. I have two questions. The first question, I'm very new to the Keldysh Schwinger formalism. This is only for this correlators is only for bosonic interaction, or you can add the fermions.
Yeah, you can. I think you can. Yeah. I'm pretty sure you can have fermions. Well, you can have these correlators and write it for when you have spin. I'm pretty sure you can do that. Yeah. If I'm not mistaken, it's just adding some external. Yes, it's just adding some extra steps to consider the spin. But yeah, it shouldn't. The results shouldn't change a lot. Yeah, it should have the same. You should expect the same to be happening. Yeah.
Yeah, I agree. But the complication is maybe because if you got in this part of section S, you have problems with the commutators in the spinor algebra, I think.
Oh, okay. Yeah. Oh, okay. So yeah. When I mentioned that you should have the same, I mentioned it in the Schwinger-Keldysh formalism. It's also valid for fermions. I'm not sure if you could have the same exact cutting rules if you have fermions. I'm pretty sure Bayer did a comment on this in his paper where he analyzed the cutting rules for the wave function formalism. Pretty sure he did a comment on that, but I don't know that if he actually computed the issue that you're mentioning. Maybe it's something that they didn't look at. Maybe.
I think. Thank you. Thank you very much.
Thanks for your question. Yeah.
I have a question.
Yeah, go ahead.
Okay. You said so there is a how can I say, set of rules to do these cuttings, okay?
Yes.
So yeah, and you say that for the sitter is okay, but you know something, I don't know, since you have done the study, some condition that you think you can relax, like translation or rotational or rotational invariance or whatever that you can think that is possible to define these things? Because you mentioned quasi de Sitter. As far as I remember, if you have slow hole inflation, thinking about the Sitter as an effective field theory, what you break is dilation. So
Mhm.
you
Wait,
have
wait.
some
I don't think
some
I
clue.
understand the full extent of the question. You're asking if this is valid for quasi de Sitter?
Yeah, if it's valid for any picture beyond the sitter, or if you know that it is possible to do it without some symmetry or whatever.
Yeah, that's a really good question. So I'm not sure. I would say that a primary condition that you need to check, first of all, before trying to compute the discontinuity, um, to check it if it's valid for quasi de Sitter, is to check this property over here for the both bulk to boundary and bulk to bulk propagators. So if this is valid, meaning that you have a nice set of properties for the bulk to bulk and bulk to boundary propagators when you interchange the sign of the momenta, and you have a nice relation with it, meaning that it's a sign. Let's say it could be I don't know, a constant appearing that's popping off, maybe. If you have a nice set of conditions for that, I would say that that you have you would have the same cutting rules. But
Okay.
this is quite naive. It's what I think at first order. We would need to go to deeper computations to see if it's actually true.
Okay, I see. Any more questions? Anyone has one more question? Some comment? Okay, so let's thank Gabriel for the seminar. Okay, thank you, Gabriel.
Thank you very
It was
much.
a very nice, it was a very
Thank you
nice
for
talk, very interesting. Yeah.
thank you for the seminar.
Thanks. Thank you guys for inviting.
Yes,
Sure.
it's very interesting topic.